Hey everyone! Today, we're diving into a question that hits every developer at some point. Why is my algorithm's performance so darn unpredictable? We're going to break down the best, average, and worst-case scenarios to give you a super clear way to analyze and understand it all. I mean, we've all been there, right? You write some code, it absolutely flies through all your tests. But the second it hits real-world data in production, it just grinds to a halt. It's super frustrating. But believe me, it's not a mystery. There's a reason for it.
The key to solving this whole performance puzzle really comes down to one single crucial idea. Not all inputs are created equal. The specific data you feed into an algorithm can completely, dramatically change how it behaves.
So we have to stop thinking about performance as just one single number. It's not a speed. It's a whole range of possibilities. And what we need is a framework to analyze this entire range. This is how we go from being surprised by performance problems to actually predicting and controlling them.
To really get the full picture, we're going to look at performance through 3 different lenses. Each one is going to give us a unique and totally vital piece of information about how our code is going to act out there in the wild.
I love this analogy. Think about it just like your daily commute, right? The best case, no traffic, green lights all the way. You get there in record time. The average case, well, that's the usual traffic you deal with every day. And the worst case, total gridlock, accident on the freeway, you're not moving an inch. See, to understand the whole journey, you got to consider all 3.
So here they are. These are our 3 lenses. The best case is that perfect green light scenario, the absolute fastest it can possibly go. The average case is what you should realistically expect on any given day. And the worst case? That's your guarantee. It will never ever be slower than this.
So first up is the best case, and we represent this with the Greek letter omega. This is the dream scenario, right? It's the performance you get when the input is just perfectly, beautifully set up for your algorithm. Now, while it's cool to know, it's usually way too optimistic to count on for any real planning.
Next, we've got the average case, represented by theta. Now, you could argue this is the most useful one for predicting what's actually going to happen. It tells you how the algorithm will probably behave on a typical kind of random set of data. This is your most realistic expectation.
And finally, the most famous of the 3, the worst case, which you all know as Big O. Think of this as your safety net. It looks at the absolute worst possible input you could throw at it and gives you an upper bound promise. For critical systems, this is the number that really truly matters. Okay, theory is great, but let's see this stuff in action. We're going to put some really common algorithms under the microscope, and you're going to see just how massive the difference between these cases can be.
Let's kick things off with insertion sort. Now, the thing that just jumps off the screen here is that huge gap in performance. Just look at that best case, omega of n. That is ridiculously fast, but then look at its average and worst cases. Both are n squared, which gets slow, really fast as your input grows.
So what's the magic trick? What triggers this incredible best-case speed? It's simple. An array that is already sorted, or at least almost sorted. The algorithm just zips right through, barely has to do any work at all, just confirming everything's already in the right place. But on the flip side, if you give it an array that's sorted in the exact opposite order, you trigger its absolute worst-case nightmare. Every single element has to be shifted all the way across the array. Same algorithm, totally different, and much, much slower outcome. Okay, how about another famous one? Quicksort. It's legendary for its amazing average case performance of n log n. But, as you can see right there, it has a hidden weakness. Its worst case is n squared, just like the much simpler insertion sort. Kind of surprising, right? And here is the kicker. What triggers this terrible performance? An already sorted list. This is a classic gotcha in interviews and in the real world. The very same input that was the absolute best for insertion sort is the absolute worst for a naive quicksort. This is exactly why you have to know what triggers these cases. So you can see, understanding these cases isn't just some academic exercise. It's about empowering you to make the right call, to choose the right algorithm for the job based on the kind of data you expect and the performance guarantees you absolutely need. This table really brings it all home. Just look at merge sort. So consistent, n log n across the board. It's predictable, it's reliable. Compare that to quicksort, which is usually faster on average, but you're always carrying that little risk of an n-squared blow-up. And then, of course, you've got binary search with that lightning-fast O of 1 best case. So let's make this practical. Let's say you're building something where you absolutely positively cannot have a performance surprise. It has to be reliable. Looking at this table, which sorting algorithm do you choose? If you're thinking merge sort, you are spot on. That O of n log n worst case gives you a rock-solid guarantee that quicksort just can't offer.
Okay, let's pull all of this together into a powerful mental toolkit that you can use anytime you're analyzing code or, prepping for that next big technical interview. So here are the key things to drill into your brain. First, you have to look at all three cases to get the full story. Remember, the worst case is your safety guarantee. The average case is your realistic prediction. And knowing the specific inputs that trigger each case, that's what separates the pros. Don't just analyze one part. Tell the whole performance story. And I'll leave you with this question to think about for your own work. For the next system you build, which one is going to matter more? The practical day-to-day speed of the average case or the unbreakable promise of the worst-case guarantee? The answer to that is going to define just how reliable your code really is.